So in Chapter 6, the applications of integrals we used it to find areas, to find volumes, work, and then we just recently saw how we could use integrals to find average values. What we'll start looking at now is some more geometric applications of integration. And what we'll look at today, in today's video, is how we can find the length of a curve. So today's topic will be arc length. What we mean by length of a curve. Say you have this curve. Think of it as if you put a piece of string right on top of the curve and then stretched it out straight and measured it along the ruler. That would be the length of our curve. However, this might be difficult to do and might lead to some errors because it's not that accurate of a measurement. If we have a polygon, then it's easy to find the length of the polygon, in other words, the perimeter, because you can use the distance formula between the endpoints. And this is going to be our strategy to set up our formula for arc length. So we'll approximate it by using a polygon, and then you increase the number of sides of that polygon and have those approach infinity, and you might see where this is going, because that'll eventually become an integral. So look at this example. So start out, if you want to approximate the length of this circle or the circumference, start with a square, and then you got a hexagon, and then you got an octagon, and you can keep going. And as the number of sides of those in the polygon increases, notice it becomes a better and better approximation of the actual length of our curve there, our circle. So that's going to be the general idea of what we're going to do. So we're going to split our curve into a bunch of small sections with delta x. Should sound familiar. In each of those, we'll take our lengths of each section. And when you add those up, that'll give you an approximation of our length of our curve. Well, we'll make those sections smaller and smaller, meaning we'll be increasing the number of them, and that eventually will be our integral. So you can see here, if we have 2 points, pi minus 1 and pi, that just means two endpoints that are next to each other. If you continually increase the number of sections you split it into, that becomes a better and better approximation of our curve. So in general, our arc length is, as our number of segments there goes to infinity, it's the sum of the lengths between our two endpoints next to each other. Well, we're going to use the distance formula to represent the length of those 2 points next to each other. So say we have 2 points. Let's think of one of them as having the coordinates xi and yi. And the other one has the coordinates xi minus 1 and yi minus 1. So by being minus 1, we know those are two of the endpoints of our segments that are next to each other. Well, using distance formula, it's just x minus x squared plus y minus y squared. That's what we have there. Well, your x minus x, that's just your change in x, delta x. And your y minus y is just your change in y, your delta y. Well, we've seen that point slope form of an equation is y minus some y1 equal to your slope times x minus x1. Well, f of xi and f of xi minus 1, those are just our y and y1s. F prime of our xi, that's just our slope at xi star. And then xi minus xi minus 1, that's just our change in x. So really what that is, our change in y is really just our derivative, which is like our slope at that point, times delta x. And the reason we'll have that is we can sub this in for delta y, giving us something that only has x's in it. So we now have square root of delta x squared. When you replace the delta y, you get f prime x delta x, the whole thing squared. Well, we can pull a delta x squared out, keeping it under the square root. Well, when you take the square of the square root, that just becomes plain old delta x. And all we're left with inside is 1 plus our derivative squared. And that's going to be the general setup for our integral. We'll put that in. We know the sum we've seen a bunch of times as n goes to infinity will just end up being our integral. So this is the important thing of what you have to know. What I just showed you a second ago is why it ends up as that. I didn't want to just give you the formula. I wanted to show you a little bit where that's coming from. But this, what I just boxed in, that's what you need to know in order to find your arc length. Now, because it can be messy to find your derivative squared, we'll usually do that off to the side and then plug that into our integral. So let's look at this example. We want to find the length on this curve from 1, 1 to 4, 8. Well, we know we're going to have our integral be the square root of 1 plus the derivative squared. And then dx at the end. Well, if we get y by itself here, we'll take the square root. That means we'll have x to the 3/2, just by taking square root of both sides. So let's see what the derivatives squared would be. So y prime would be 3/2 x to the 1/2. When we square that, we'll get 9/4 x. So that's what we'll put in for f prime x squared. When we do our integral, our x values, we're going from 1 to 4. And we're going to have the square root of 1 plus. We just determined that our derivative squared was 9/4 x. And then we'll have our dx. So it's usually helpful to do that derivative squared off to the side. And sometimes you can even do the plus 1 in there if it'll neaten things up off to the side. And then put it under your radical in your integral. Well, this is something we're going to have to use u substitution for. So we're used to seeing just a plain square root of x. So we'll let u equal 1 plus 9/4 x. And du will then equal 9/4 dx. Well, our leftover part is just a dx. So we'll multiply both sides by 4/9, and we'll get 4/9 du equals dx. This means when we do our integral, we're going to have square root of u du, and then we'll have to put the 4/9 out front. So that's really u to the 1/2. U to the 1/2 will become u to the 3/2, and we'll put 2/3 out front. Don't forget we have the 4/9. We'll replace what u really was, so we'll have 4/9. We'll have 2/3. U was really 1 plus 4/9 x. Or sorry, 9/4 x. And that is to the 3/2. And we're evaluating from 1 to 4. So when we plug in, we could pull out the 2/3, in fact, if we wanted. When we do that, we'll get 8/27. So this got pulled out front. When we plug in the 4, 4 times 4/9 is just 9. 9 plus 1 is 10, so we'll have 10 to the 3/2. And when we plug in 1, we'll have 9/4 plus 1. Well, 1 is 4/4, so that'll give us 13/4 to the 3/2. Now, this is an exact, oops, this should be a minus, sorry. This is an exact answer. Okay, remember, this year, if you have something that's equivalent, you can leave it like that. Like you could leave it as 2/4 and not 1/2. So I would suggest just leave it right like this. Don't go any further. You could write 10 to the 3/2 as 10 square root of 10. You could break down the 13/4 to the 3/2 if you wanted, but I would say it'd be easiest, just leave it right like this. Now this could work with y's as well. Okay, you would just flip-flop everything. You'd have dy and you would have your function in terms of y, and you would have to make sure you have your y values in your integral. So it can be done either with x's or y's, either way. And depending on what they give you, that might tell you if you want to do it with x's or y's. If you have something where you can't get y by itself very easily, then you might want to do it as y's instead of x's. All right, so last example for this video. In this example, we are going to use a method that will become very common when working with arc length. So we've seen we need to first find what is the derivative, square it, and then add 1 to it, and that's what will go under our radical. Well, y, I'm going to rewrite as 1/6 x cubed plus 1/2 x to the negative 1. That will help us find the derivative. So y prime, 3 times the 6 will give us 3/6, which is 1/2, and we'll have x squared. Negative 1 times a half will give us negative 1/2, and we'll have x to the negative 2. Well, I'm going to rewrite that y prime as now 1/2 x squared minus 1 over 2x squared. Well, we have to square it now. To square the right side, you've got a FOIL. So let's do that off to the side. We'll have 1/2 x squared minus 1 over 2x squared times itself. 1/2 times 1/2 is 1/4. X squared times x squared is x to the 4th. A half times a half times a negative half is a negative 1/4. X squared on top, x squared on bottom cancel out. Our inside terms, negative a half times a half is a negative 1/4. X squared on top, x squared on bottom, those cancel out. And then a negative a half times a negative half is a positive 1 over 4. And we have 2x squareds on the bottom, so we'll have x to the 4th. Well, this means when we combine our like terms, this will give us 1/4 x to the 4th. We'll get a negative 1/2 in the middle, and we'll get plus 1 over 4 x to the 4th. Let's go ahead and add our 1. When we add 1, it'll combine with the minus 1/2 in the middle. So our y prime squared plus 1 is now 1 over 4 x to the 4th plus a positive 1/2 plus 1 over 4x to the 4th. Now this is where the common method comes into play. Notice all that changed is our middle sign there changed from a negative 1/2 to a positive 1/2. If we go back to where we FOILed it out, if these signs had just been pluses instead of minuses, we would have gotten that positive 1/2 in the middle. So what that means is this thing actually factors. It factors into what we had up here, but just with pluses instead of minuses. This really factors into 1 over 2x squared plus 1 over 2x squared times 1 over 2x squared plus 1 over 2x squared. So the same thing we had before, but now with pluses. And it just switched that sign. And you'll see this method a lot. You'll get a negative 1/2 in the middle. You'll add 1. It'll give you a positive 1/2. So the factors will just be the same as before, but with pluses instead of minuses. So we can actually rewrite this. Our part that goes under the radical is just going to be 1/2 x squared plus 1 over 2x squared, the whole quantity squared. And again, that's the part that's going under the radical. So we'll see in a second why it's so important to write it like that. Well, we have the square root of 1 plus our derivative squared. We just rewrote that as 1x squared plus 1 over 2x squared, the whole quantity squared. This will be a dx, and our x values we're going from are 0.5 to 2. Well, notice how nice this is now. We have a square root, and we have a squared. Those will cancel out. So we just are from 0.5 to 2. We'll have 1/2 x squared plus 1 over 2x squared dx. To make it easier to take the antiderivative, I'm going to rewrite it as 1/2 x squared plus 1 over 2 x to the negative 2. And now we can go ahead and take the antiderivative. We'll get an x cubed, so we have to multiply by 1/3 out front, which should give us 1/6. Our x will now be to the negative 1, so we have to multiply by 1 over negative 1, which is negative 1 out front, which will give us negative 1/2. And this needs to be evaluated from 0.5 to 2. So we will have 1/6 times 2 cubed minus 1/2. Remember, x to the negative 1 is really 1 over x, so we'll have a 1 over 2. Minus, put it in parentheses, 1/6 times 1/2 cubed minus 1/2 times 1 over 1/2. 2 cubed is 8. 8 times a 6 will give us 4/3. 1/2 times 1/2 is a 1/4, so we'll have negative 1/4. 1/2 cubed is 1/8 times a 6 is 1/48, and we'll have to negate it. And 1 over 1/2 is really 2. 2 times 1/2 is 1, so we have a negative 1 that we then negate, which makes it a positive 1. When we combine all our like terms, we can get 48 as our common denominator. The first thing we'll multiply top and bottom by 16. So we'll get 64 over 48 minus minus 12 over 48. Minus 1 over 48 plus 48 over 48. So we'll have a minus 13. If you take that away from the 64, that'll give us 51. 51 and 48 will give us 99 over 48. You can divide each of those by 3, which will end up giving us 33 over 16. And that is the length of our curve from 0.5 to 2. Again, the big key here is to notice when you have that minus 1/2 and you add your 1 to get a plus 1/2. It's just your original factors with pluses now instead of the minuses. So you can write it as a quantity squared under your radical. That way the square and square root cancel out. And that, again, will be a very common method that we will use. That's all for today's video. We'll see you next class period.